6:05. Hi, everyone. I was waiting to say that for a long time since we decided to go with this meetup. Thanks for attending. I'm really, really excited that we are doing it. And I do hope that we will keep on doing it even after the coronavirus has gone, when it will be gone. Myself, Kelvin, and Sean, we've been talking and creating plans who is going to say what now, because it's our first time to do full remote, not when the speaker remote, but when everyone is remote. So we fought for hi everyone, and I won. It was not easy. But then we decided that Kelvin will do the introductions, and Sean will kick out anyone who will consider to be a bad actor. So be prepared to behave, me included. So no further ado, Kelvin, would you like to make a round of introductions? And Kelvin, yes, no? As everything goes, it didn't go as well. We can't hear you. You can hear me?
No, we can hear you, Kelvin.
Okay.
You're fine.
Okay, so maybe I'll slow start the introductions, and Kelvin will interrupt in the middle as he tries to go through his technical difficulties. So Yunan, software engineer by training. We had a chance to work together on some stuff during our PTM times. Since then, a lot of things went by. And nowadays, he is an expert in all things Scala, Akka, and even Lightband. So I don't know if it will be considered a good intro, but I guess no further ado, Yunan, thank you for presenting.
Yeah, thank you. That's a very good introduction. Thank you. I actually see quite a few familiar faces. So to all the people who know me, hello, and to all the people who don't know me, nice to meet you. So I guess I'm gonna get started. We're not gonna wait for Calvin, right? Well, all right. So I spent some time to build a project, and it's a graph database using Akka typed. It was both for me to learn the new Akka typed API, and also try some of the things that I don't normally get to try using some of the Akka features. So let's just jump into it. Akka is a popular toolkit for Scala developers to build concurrent and distributed systems. And in this talk, we're going to talk about how I was able to use some of the more interesting features to build a simple distributed graph database. And we are going to go through how and why I used each one of these Akka features to build it. And by the end of this talk, I hope you learn something from me, and you also learn about these features in Akka. And I also hope you use these features in Akka to build interesting projects. So I guess the first question is, what is a graph database, since we're going to talk about a graph database? A graph database is a database that stores information about a bunch of nodes, as well as the relationships between one another. And that is if there is one. If there's no relationship, then it doesn't get recorded. And these relationships are stored as edges, or represented by edges. Both nodes and edges have types, and they also have properties. And these types and properties can be queried. So, for example, if you see on your screen here, we have 3 different nodes. Let's take this one, for example. It has 3 properties. Has an ID, has a name, has an age, and then it has a to relationship to this node of ID2. And then for this edge, it has an ID, it has a bunch of other properties. And then, yeah, that's the basic idea. And each of these nodes have some relationship with the other one, as seen here. So the second question to ask is, why would you ever want to use a graph database? And the answer to that is basically when you use relational databases or even some NoSQL databases, you're going to have to follow a rigid schema. And the schemas are designed to serve some dedicated purposes. So for example, serving some kind of query or serving kind of retrieval of information. But when you receive unexpected questions, it's actually hard to find an answer. So for example, here, when you're looking for the connection from actor A to actor B and actor C, and sorry, these are not Akka actors. These are just actors in movies. So you're going to have to rely on many different join operations or something like a Spark job to get you the answer, to find you the relationship between actor A and actor B and C. And if these unexpected questions become new requirements of your system, it is also very expensive to refactor things. So you have to redesign your schemas, and you have to try to avoid using a lot of join operations to get you an answer. And then once you have it built, if you have, again, a different question, then you're going to have to refactor your system again. So that's where graph databases come in. They are really good at finding these complex answers to these complex questions. So again, for example, here, when you're looking for this relationship, all you have to do is to trace through all the nodes and basically find the shortest path between actor A and actor B, or actor A and actor C. And you can, of course, use a graph database to build many different interesting systems, such like a recommendation system, or an anti-fraud system, or content management system. And there's way more, but those three are the most common ones, I believe. And next, we're going to talk about Akka. So the first question is, again, what is Akka? Akka basically allows you to use the actor pattern in Scala and Java. And there's also .NET, but not going to talk about .NET here. So in the actor pattern, each actor is a unit of computation. So instead of calling functions inside of actors, what you do is you do message passing. So the actors rely on message passing to receive messages and process them sequentially. So this allows the system to get rid of logs, as well as keeping the state of an actor in CPU cache, making the message processing much faster. So if you look at the image on the left, you have three different actors. The main Hello World main actor, and it spawns two other actors, Hello World bot and Hello World. So these two actors, Hello World bot and Hello World, talk to each other by passing messages. So when Hello World bot sends a message of a greet to Hello World, Hello World can process this message and reply with a message of greeted. And on the image on the right basically shows how message passing and how a sequential processing of these messages work. So for example, when you have three actors, actor 1, 2, and 3, and you have actor 1 sending a message A to actor 2, and then actor 3 sending a message B to actor 2. Your actor 2, when it receives message A, may not be able to process message A right away. It has to wait for the dispatcher or the thread pool to give it available resources to process these messages. So what happens here is that actor 2 puts message A on the mailbox, and then also puts message B on the mailbox. So when it has the available resources to process these messages, what it does is it retrieves message A from the mailbox, and then finish processing message A. And then once it's done, it dequeues message B from the mailbox, and then starts to process message B. So the nice thing about this sequential operation is that the sequential processing is that when you put this actor into a CPU to get processed, the context or the actor state is put into the CPU cache. And you can configure your dispatcher to process multiple messages for an actor. So then your actor context or your actor state never needs to leave the CPU cache. And you can just basically process these messages using the same cache in your CPU core, one of your CPU cores. So this prevents a lot of cache misses or cache evictions inside of your CPU cache. And that makes processing much faster, because when your CPU core is reading from the CPU cache, it is super fast. And when it needs to read from the main memory, that's like magnitudes of magnitudes slower. So the final question that I'm going to ask for this project is, why do we need to build a graph database using Akka? And I actually have 3 answers for it. One is that graph nodes are modeled by actors nicely. So message passing between actors and the distributed nature of Akka actors in an Akka cluster serve all possible queries in a graph database in a distributed fashion. So that basically means you can have your graph database in many different machines and still be able to do the processing. And you can also maintain the graph edges as state inside of your actors. And you can keep the type of the edges, the property information. So you basically end up with the same image as this one, as the graph image over here. And yeah, so the 2 graphs that I put here, I'm basically trying to say I see a lot of similarities between these 2 images. That actually triggered the initial thought why I wanted to build a graph database using Akka. Okay, this graph seems kind of, this image is kind of low res, but let's just go with it. So the second answer for this question, for why we want to build a graph database using Akka, is like a slight improvement using Akka actors over a graph database is that actors are naturally FSMs. Each state is constructed of some data and a behavior. Especially using the Akka typed API, it's easier than ever to model your actors using FSMs. And if you've, quite a few of you have worked with me before, and you already know that I love using FSMs to build systems. And I hope you try it too. It's actually super nice. But what I'm trying to say here is actually actors have both data and logic. So when you need to retrieve a value, do some calculation and save the value back, like with any kind of database, including a graph database, all you have to do with actors is just sending a request to the actor. And the actor handles the calculation based on its own state, and then it also updates its own state. So instead of 2 round trips, sending a request to retrieve the data from a node, get the result back, do your calculations based on the information that you just retrieved, and then save it back. All you have to do is just sending the request to an actor. And it might be quite small for a few transactions, but for a system with a lot of traffic, you're actually saving quite a lot by avoiding the second round trip. So the example here, the image over here on the screen is a circuit breaker. So for a circuit breaker, you have 3 different states: the closed state, the open state, which is the initial state, and then the half open state. So you have different ways to transition from one state to another, and this is the same inside of your actor. When you receive different messages, you can transition your actor into a different state, and in that state, it can handle more messages, and it's able to transition itself into other states. So that's the nice thing about using FSMs and FSMs inside of actors. And finally, the final reason that that is also the most interesting to me, why I wanted to build an Akka graph database, and that is actors are able to react to system events in a more meaningful way, and I will show you what I mean in a live demo. Let me actually stop this, and I think I need to share my, oh, no, actually, I'm okay. I hope you can see this. So, okay, so what I have here is a recommendation system. And inside of this recommendation system, I have a bunch of content. Each content is a node in the graph database, and each node has a bunch of tags. So what I'm going to do is, or what the system does is it tracks what a user does inside of this graph database, and it uses the tags to make recommendations for other nodes that you can visit. So these are all the nodes right now in the system, and I also have a graphical form of these nodes. And each on this image here, I hope you can see it. Each dot is a node or a piece of content inside of the system. And like mentioned before, each one has a tag, and you can see that the tags on top. And for example, this one has the tag speaker B, messaging, developer, Google, smart, and AI. So before this, I wanted to ensure that the system works. So I actually already did some recommendations or visiting different nodes. So there is some connections already made, some edges made inside of this graph database. So I'm using a completely fresh user. It has not seen any content inside of the system yet. So I can go into one. And this one is the one over here. And because I've already done visited some of these nodes before, there is an edge to each one, to 8171 to 81. And that's why I'm seeing this new this recommended node inside of this page. So then I can click on this this recommended node, And then I will stop seeing the recommended nodes because there's nothing being recommended. There's no data available for the node to make a recommendation. So I can click on something else. I can click on this. And I can continue to click on other things. And this. So I've visited a whole bunch of nodes. Give it a second. So as you can see, I'm making a bunch of, adding a bunch of edges to my nodes. So from 7.1 to 8.1 to 5.2 to 5.9 and to 5.0. So if I log in as a different user, and the process of logging in as a different user is basically passing in a different user ID to keep it as simple as possible. And if I go to like one of the nodes I've seen before, I'm seeing recommended content, and then more recommended content, and even more recommended content. So all these recommended content are based on the edges that I've saved inside of these nodes. And when I have a lot more user using the system, more edges will be created. And then as each node collects more user information, it will be able to use these information to make more useful recommendations. So for example, if you see that a user is interested in climate, you can make you can follow what other users who are interested in climate and recommend the things that they see. So yeah, that's it. So several other features on this page is I also have a trending recommendations. So this is basically the most popular nodes that are being seen by people at any moment. So I'll talk about how this is built in a few minutes, in a few slides. So any questions so far? All right, so let's continue. The concepts or the ideas that I've used in building this thing, the graph database, as well as the recommendation system on top of the graph database, are basically three things. One is distributed system, and I believe most of you already know what a distributed system is. We basically just have a bunch of actor systems on top of many machines, and these machines are able to talk to each other and work with each other to do calculations and processing. And the second is event sourcing. So the basic idea behind the event sourcing is that by persisting all events of an entity, and the entity is basically a common name of the thing that you're trying to build. So in this case, in a graph database, an entity is basically a node. So by persisting all events of an entity, your state can be recovered by replaying these events. So this gives you the freedom to change the logic when replaying the events to fix any bugs or adding any new features that you want into your system. So for example, if you're seeing a bug in your system and it's making a wrong calculation for your current state, instead of your state is already wrong, and instead of giving up on that state, what you can do is you can fix your processing logic, replay all the events, and use the new logic and also the events that you replay to calculate a new state, and that new state will have all the right information in it. And then the final concept is called CQRS, and CQRS stands for Command Query Responsibility Segregation. So what that basically means is you're going to have two sides, the write side and a read side for your system. So the write side should be good at handling writes, and the read side should be good at handling reads or queries. So it's actually recommended to use CQRS in an Akka application because individual actors are really good at handling its own messages. But when you are trying to do queries across multiple actors, there's no easy solution. And, or I should say there's no single solution that solves all the problems. And the best way to handle these queries is to implement a read side for every type of query that you're going to have. So in the case of the recommendation system that I built, the trending nodes, this is built by CQRS, and it basically has its own read side to query, and it's able to recommend things based on those queries. And I'll get into details again in a few slides. So to implement these three concepts, the distributed system, event sourcing, and CQRS, I'm utilizing Akka cluster. So inside of Akka cluster, there are a few things, a few interesting features. One is Akka persistence, and that is used for event sourcing. And inside of Akka persistence, you will be able to tag your events, and that basically allows me to retrieve these events and build my read side based on the events, and that is part of CQRS. And in addition to persistence, I also have a cluster sharding. Cluster sharding basically allows me to put my entities onto different nodes or different machines in a system. And finally, we have the persistence query, and that is basically a feature that Akka provides to query the tagged events when you're persisting the events. So I'm going to jump into details of these things in the next slide. So the first thing that I want to talk about is the right side of this system. So like mentioned in the previous slide, cluster sharding is used to distribute my entities into different machines. So in this graph here, each actor system lives on a different node, or they can live on the same node, it doesn't matter, or on the same VM or in different VMs. But each actor system is its own JVM. And when I use Akka, when I put these actor systems inside of Akka cluster, what is happening is these actor systems are able to talk to each other, and they will be able to form a cluster, do leader elections, and keep the state of all the members inside of the cluster up to date. And Akka cluster basically handles all that for you, so you don't have to worry about any of that. And when I'm for cluster sharding, what I have is inside of each actor system, I have a shard region. So this rectangle here is a shard region. And what shard region does is it keeps a bunch of shards inside of itself. And then each shard has a has a bunch of entities. So when you are trying to handle a command that has some sort of ID for your entity, and you're basically trying to send that command to the right entity, what is happening is you're sending that command to your actor system, and then the actor system pass it on to the shard region, and shard region will look at the ID. Well, first retrieve the ID from the message, look at that shard ID, the entity ID, and it has information about different shards based on the hashing algorithm. And by default, Akka has a hashing algorithm, so you don't have to worry too much about that if you don't want to. And it's going to be able to find the shard that the entity is on. And then it also has information of where that shard is inside of the cluster. So it's able to send that message to the right shard. For example, it could be on this system. And then once it gets passed to the shard will find the entity and then pass the message to the entity. And then the entity will be able to handle that message and reply on that message. So the next thing is Akka persistence. So when you have these messages passed into the entities can decide whether to generate events or not. So anything that has happened to a system becomes an event, and then the entity will send the events to a persistence layer. This persistent layer can be Cassandra, it can be a JDBC, or it can be another type of storage. And all it has to do is it needs to be able to replay these persistent events when an entity dies or a new entity is created. So yeah, that's basically Akka persistence. It's when you persist all the events to a storage layer, you're doing event sourcing, and like mentioned before, you'll be able to recover them and add your new logic into your system, or fix any errors in your system by replaying the events and changing the logic at the same time. So the right side is only good at handling messages for each individual entity, like mentioned before. So when you want to get multiple entities involved, you have to use the read side, like mentioned in the CQRS section. So next, we're going to talk about the read side. So when the events are persisted by the system into the storage layer, you'll be able to tag these events. By tagging, all you're doing is just giving different names or different tags to the events. And then the events will be persisted to Cassandra or the storage layer. And then you'll be able to query these events based on the tags. So when you use persistence query, which is a feature provided by Akka, you get these tagged events from the storage area, and you'll be able to use some kind of streaming tool, such like Akka Streams, to process these events. Maybe get rid of the information that you don't need, or maybe find some kind of schema that is best for your query and save it to another storage layer. This storage layer can be the same as the one that you're saving the events, or it can be something else. A good idea is mostly using some kind of SQL database. Yeah, SQL databases. So by using SQL, you have more available queries that you can use. in your system. So that is it for the read side. So before I jump into any more details, any questions so far?
Hello.
Hey,
do you hear me?
Yep.
Hi. Let's say my workload increase.
Yep.
And so to accommodate the heavier workload, I increase the number of actor system.
Sure.
Let's say multiply by 100, let's say.
Mm-hmm.
And how about the storage system on the write side and the read side? Would they remain one single instance of storage system, or can I multiply them as well?
So your question is, if you are increasing the load of your system, and like by adding actor systems into the cluster, what do you do when the data is so much that, like, how do you handle that new load in your storage layer? That's your question. Okay. So that's why I put Cassandra here, because you can also add Cassandra nodes. So if you're adding like two actor systems into your cluster, and your load is overwhelming your current Cassandra cluster, you can also put a few more nodes into your Cassandra cluster. And then it's the same for your read side database. This read side database you can decide what to put into it, and if you have a lot of load into that read side database, maybe think about not using SQL, use Cassandra as well, or use some other kind of database that can handle the load.
So in other words, the storage system remain a single cluster, but with more nodes.
Yes.
But not like 2 or 3 cluster of storage.
You can do that too. If you for your read side, you can, for example, you have three types of different queries. You can put each type of query into its own database. So you can have over here 3 different Akka streams writing to 3 different storage layers, and each one is for a different query.
So I have a question about, I don't know, can you hear me?
Yes.
Okay, I have a question about the read side and the write side. What's the difference between it? So is it the same Akka system or 2 different ones?
It is. So you're talking about this system over here that I have on the read side, right? Okay, so this system can be the same system as your write side, or it can be a different thing. It can be another microservice or some kind of API layer that serves your data to another system. Basically, can be anything.
Okay. So maybe not the very relevant. So what's the difference between Akka and the Kafka?
Okay. So Akka is basically a toolkit for using the actor pattern, the actor programming pattern. So when you're using actors, you can do many interesting things well, basically you use your actor systems to build concurrent systems. But Kafka is a completely different thing. Kafka is a tool for streaming. So basically, if you're trying to put some messages somewhere for other systems to consume, you can put it on Kafka, and you can even here when you're trying to put your events into some kind of system. And you want other system to consume these events, you can, instead of putting them on Akka streams and writing them to a different database, you can put them on to Kafka. So then other systems can consume that Kafka instance and do whatever they want.
Okay, thanks.
No problem. Well, I'm actually done with the presentation, but if anyone wants to see any coding, let me know, and I'll jump into some of the more interesting things in the code. But otherwise it's done.
Well, Yunan,
Yep.
the graph database, actually, there is no graph database, right? The graph actually is the actor themselves.
Yes, exactly. So you're by connecting the actors together, I get I get the graph database.
Yeah, but so then, what is the power of the graph query then? For example, if you were asking like who has no friends or who has a lot of connection or something, how can you design this kind of query?
Sure. So inside of my Akka graph database, I basically support all kinds of graph queries. So for example, if you're looking for like some kind of node that has that knows some other nodes. So for example, here the node ID 1 that knows another node who has the name of Bob. You can write it into a query and put it into the system, and then you'll be able to find that these two nodes and the relationship between the two. So that is supported inside of my code by using some kind of by using another actor, a query actor on the outside. So the query actor will be able to find the initial node that you're looking for by going to the read side to search for that node or a bunch of nodes. And then for each node that is returned from the read side, it sends a message to that node, check to see if the edge that you're looking for is available. And then a bunch of other nodes will be returned, and the query actor is going to send more requests to these returned actor nodes, and then look for the name Bob. And if it's able to find that node, it's able to return a result for that query. If not, then it's an empty result set.
That sounds really expensive because that query actor had to visit almost every node in order to find the answer.
Not really. If you're if you're looking for the shortest path, then yes. If you have to go through basically all the nodes to find the shortest path between two nodes. But I don't believe there is a better way unless you somehow cache some of the results for shortest path between between nodes. But for a edge query or a node query or a graph query, because you are passing in the edge information, you'll be able to query by these edges inside of your actors, and you will be able to eliminate a lot of the nodes inside of your system right away. And initially you don't have to start with all the nodes inside of your system. All you have to do is, as long as you're passing in some kind of information for that initial node or initial nodes, because I have a read side, and the read side supports a query of these nodes, I'll be able to retrieve all the nodes, for example, that have the name of Alice. You see what I mean? So you're only going through a subset of nodes inside of the whole system.
Okay, thanks.
All right. So
Yunan, we want to see the code. We want to see
Yes.
the code. A little bit of the code.
Sure.
The most interesting parts.
Let me present a different thing. Present window. Okay. There is actually quite a bit of code for this recommendation system, and you're going to see a lot of print lines and other stuff that I have, because I was actually just fixing the system right before the presentation. But anyway, so
Yunan, just before you proceed, you're in a good company. I don't know if there were other people this Saturday who could listen to Martin Udersky talking about Scala 3.
Yeah.
I had the pleasure to, and he mentioned a couple of times how much print line code he has. So you're in a really good company.
Okay. Thank you. Yeah, so this is, of course, the main class for the database, for the graph database. And I'm basically loading a bunch of stuff. I'm starting the actor system. And something interesting here is that I'm starting the untyped actor system first. So if you follow Akka, you might already know that in Akka 2.6, where in Akka is recommending to use Akka typed, actor typed, or typed actors. So all the things about the actor system become typed. But then over here, I'm starting a untyped actor system, and then I'm because that is needed for Akka HTTP. I'm still using Akka HTTP 10.1.10, so it's kind of an older version of Akka HTTP, and I haven't had the chance to upgrade the Akka HTTP to the latest version yet. And Akka HTTP requires untyped actor system. That's why I have it here. And then next, I am you can have the two coexist, the typed system and untyped system inside of your actor system. So over here, what I'm doing is I hope that the code is actually big enough to see. Fix that. Whoops. Okay, now it's bigger. Okay, so by calling this to typed, I have a typed actor system. So then using this typed actor system, I can start the cluster. This cluster is started in the config, and then I can start the cluster sharding, and I have the settings for cluster sharding. I'm actually not using it, but in the future I do plan to change the settings to achieve some special features. And then I'm starting the shard region, like I mentioned before in the slides. So the shard region will contain a bunch of shards inside of this actor system. So to do that, to start the shard region, all I have to do is to call init on sharding and pass it the key for my entity, and also tell it how it's going to be able to start an entity inside of the shard or the shard region. So to do that, basically you pass in the behavior of your actor, and I'll talk about that soon. And then you also pass in the persistence ID, and whoops, and you tell it how to retrieve the entity ID of that entity. So I'm setting a role here for this shard region, and that is because I want to use a proxy for my shard region. I actually have a Saga microservice outside to manage some of the requests in the recommendation system, and that Saga system basically has the proxy shard regions inside to pass messages to Graph and to other microservices. So yeah, let me just jump into this real quick. I'll try to make this quicker. I'm sorry. So when you want to use Akka persistence inside of cluster sharding, you can use this predefined behavior for your actor, and that is the event sourced behavior. And I wanted to enforce that every message that I pass into this entity has a response. So I'm calling this function to create the behavior, and this basically enforces or checks to see if I'm replying on all the messages that I'm sending into this this entity. So all you have to do to start this this actor is to describe the event source behavior. And for that behavior, there are three things. First is the persistence ID, or the entity ID of this entity behavior, and you pass in the initial state of this behavior, and you pass in how to handle the commands for this entity. And then finally, you pass in how to handle the events that are persisted to the storage layer for this entity. So after this is created, I'm calling two more things. One is with retention. So when you are persisting every event for this entity, firstly, you might have a lot of events for this entity, and if you recover all these events for every time this entity is restarted, it might take some time to recover the current state of this entity. So what you might want to do is to snapshot the current state, and then when you recover this this entity, instead of replaying all the events from the very beginning, you can just load the snapshot, and then replay all the events after that snapshot was made. So in this case, I'm snapshotting every 20 events, and then I'm keeping the past 2 snapshots. So for example, if I make a snapshot of the current state, and then 10 more events were persisted by this entity. When I try to recover this entity for any reason, for a failure in the system, or a node dying, or a networking problem, what happens is this entity will look for the previous snapshot, and then it will recover that snapshot, and then recover the 10 events that it persisted before it died. And then if you send it another 10 events, it's going to do another snapshot, and then this process continues. And by keeping 2 snapshots, you're keeping 2 snapshots. Any older snapshots will be deleted. Then you will also be able to delete the events, the older events, based on your a snapshot sequence ID. And that I don't want to get into that, because that's just more stuff to explain. And then this with tagger function is basically giving me a way to tag my events. So I only care about 2 different events in the system. One is the graph node updated event. This is for me to keep track of all the nodes created or updated inside of the system. So basically, by replaying these events, I'll be able to maintain a read-side database of all the nodes that I have in the system. And you can query that node by using the node type, and the node ID, and the node properties. And then the second event is the number of clicks that I get on this node to make recommendations, to find the trending nodes in the system. So again, I just give it a name, a different name for each one of these events. And for all the other events, I'm not tagging them. They just have empty tags. So when I'm trying to retrieve them, I will not be able to because they don't have any tags. So yeah, that's basically it. That's basically how you can create an Akka cluster, Akka cluster sharding, persistence, and tagging the events, so you can do persistence queries in the future. And yeah, and basically the command handler and event handler are just logic. So whatever commands that I want to handle inside of this entity, I will handle them. One interesting thing is if you've used Akka typed after 2.6, after Akka 2.6, you might be aware that you create behaviors for, you basically create FSMs, and for each state in the FSM, you create a new behavior for that state. And inside of that behavior, you can handle your messages in different ways. But inside of event source behavior, you don't do that. You don't create behaviors anymore. Instead, you have the state and the command for this entity, the state and the command. And what you want to do is you want to match on the different states and then process those commands in different ways. So you still have your FSM. It's just a slightly more verbose way to handle different messages in different states. So yeah, and for the read side, I'll just go through it super quickly. All I'm doing is, oops. So on the read side, all I'm doing is I'm starting a read side, a singleton actor for each of my read side. And for example, this one, the node read side. I'm basically saving all the nodes into a database, into a different database to query for queries. So what I'm doing here is basically I'm querying. Where's my persistence? Persistence query. Okay, so I'm telling the system that I'm doing a persistence query, and then I tell it the tag that I want to query for, and this is all you have to do: query by this tag, and you get all the events based on this tag. And another thing is you need to pass an offset to it. So this offset is based on timestamp, or it can be empty. If you pass an empty offset, what happens inside is starting from the very beginning, the beginning of the events. And then you have to handle the offsets yourself. Every time you process another event, you persist the offset of that event into your read side, or into in anywhere, any storage area that you want to use to persist the offset. And then every time you are starting the events by tag, you need to go retrieve the previous offset. So you're kind of doing some kind of similar to Kafka. You persist your offset somewhere, retrieve the offset, and then use that offset to retrieve the events. And that's it. Anything else that you guys want to see?
I have a question, if you don't mind.
Please.
Tagging, is it a way to have filtering the events at the time when you read them out of the event queue or something?
Yes. So, like mentioned, in this with tagger function here, I only care about these two events because I want to create a read side projection for these two things. So I'm tagging these two events based on a name that I pass in, and when I retrieve those events based on the name, and also all these events are in order. So if you're doing two graph node update events, the two events will be in order. So you have to start somewhere, and that somewhere is you basically have a stream of events of this event, and you tell it the offset to start from somewhere, and you tell it the name to know which stream that you want to read from.
Let's assume I forgot to tag it. What would happen at the read side?
In that case, you don't get anything.
Or I may get like all of them, and then
it's possible.
I may process the wrong.
Yeah, it's possible to get all of them. You can do that. But normally, I would suggest to tag your event and.
Yeah, of course. But well, the point is to wonder what the usefulness of tagging. Okay, all right.
Yeah.
So my second question would be, where is the cooperation between the type actor or the type actor system and the untyped one, the classic one, which you initialize at the beginning?
That's a really, really good question. I forgot to mention that. So when you create your behavior, actor behavior, you have to pass in a command type that this behavior can handle. So in this case, I can only handle graph node commands. And if I go there, I can see that I have a sealed trait for this command, and I have several different commands extending this graph node command. And so basically that means for this actor, I can only handle these 7 types of messages, of commands. If you try to send this actor anything else, you will not be able to, because the actor ref is typed as well. Like you can't even compile the code if you don't have the right type information.
Yeah, that I got. That is how Akka type work. Okay,
yeah.
But at the beginning, you initialize one actor, which is the classic one.
I don't have a classic actor, but if you're
the rate demo line 28.
28. This. Yeah. So this is only used as an implicit for the Akka HTTP code that I have to receive a command from the outside from the API. It is not being used inside of the system anywhere, except when I need the typed system from the untyped system. And if you remember the untyped actors, you can create an actor ref without a type, and you are able to send that actor ref any message, any type of messages. And you also use props to start it. But for your typed actor, you use a behavior. You basically call the behavior, and you pass in a bunch of things, the props for that actor, to initialize the first behavior. But for event source entity, the only thing that is needed is the persistence ID, because it's using this persistence ID to go back to the database, retrieve all the events for this persistence ID, and replaying those events. So there is no, you don't need to pass in anything else, and that is because the shard is handling the behavior for you.
Okay, so meaning that the untied logic of that application, that means the graph database, is handled by the Akka type actor, right?
Yes.
Line
Yes.
32. And the only time the classic actor system can be played is when you send the result over HTTP.
Well, I mean,
so let's say
Akka HTTP uses Akka streams, and Akka streams uses actor materializer, or actor materializer. And for actor materializer, you have to create from the untyped actor system. That's why I have it here.
Yeah. So
But
let's say if you uncomment line, if you comment out line 28, what would happen to the application?
It will not work because, okay, so everything else will work except Akka HTTP, and that is because I'm using an older version of Akka HTTP. That's the only thing.
That means the web browser, when you show at the beginning, the web browser that show the dot and the link.
Yeah, that is actually through a different microservice. But yeah, that's basically it. If I'm sending a command through HTTP, then yeah, that wouldn't work.
Okay, cool. Thanks.
All right, I think that's all. Unless anyone has any other questions for you.
And if you would like to look at more details, I actually have a Medium article on this project, and it's I'll send the link to chat, and whoever wants to look at this project in more details, please do.
Awesome. Thank you so much, Yunan. It was great having you here, and thank you everybody for your questions.